Okay, so this is exam 2 for physics 202. Let's see here. Electric potential is a measure of energy per charge. This diagram shows a collection of charges. At what point is the potential equal to 0? Okay, you want to find points that are equidistant from opposite charges. So for example, these two, the potential does not cancel out. In these two, these distances are equal, so that potential cancels out. Those two are equal, so that cancels out, and those two are equal, so that cancels out. So that is our answer, is that B. If we look at some of these others, for example, here at C, that distance is different from that distance, so the potential due to the -1 and +1 don't cancel out. And then similarly over here, this distance is different from that distance, and here, for example, this distance is different from that. So B is the right answer. Proton, an electron in a constant electric field is shown. You release an electron and proton at a point equidistant between the plates. Which particle has more kinetic energy when they cross the plates? All right, well, they're both going to experience the same change in potential, and they both have the same charge. And I know that this energy is equal to Q times delta V. So they're both going to have the same kinetic energy. So D is the right answer. This following is a plot of potential versus position. You release a proton. That's a positive charge. Now remember, with protons, if I think about my plates here, I have high potential, that's the positive side, low potential, that's the negative side. A proton in between these two will move from high to low potential and move in that direction. So here, if I have a proton here, it wants to move from high to low, so it's going to move in this direction. All right, so it's going to go to the left, see. The capacitance of a parallel plate capacitor can be increased by not this. Remember, capacitance is epsilon naught A over D. Actually, put our kappa in there as well. Increasing the charge doesn't change it. Decreasing the charge, increasing the plate separation. So if I increase this, that causes the capacitance to go down. So it's not that. Decreasing the plate separation. If I decrease this, that does increase my capacitance, so 4. And decreasing the plate area, let's see, if I decrease this, that makes this also decrease, so that's not the answer. So the answer is C. What point is the potential greatest? Okay, well, V is KQ divided by R, so where R is the smallest is where our potential is the greatest, so A is the right answer. Parallel plate capacitor initially has a potential difference of 200 volts and is then disconnected from the charging battery. If the distance between the plates is now doubled, what is the new value of the voltage? Okay, so I have this capacitor. It has a certain amount of charge. All right, that amount of charge, when I remove the battery, this amount of charge remains the same. It doesn't change at all, so it's constant. However, if I double the distance between the plates, C is epsilon naught A over D. If I double this, that means the capacitance goes down by a factor of 1/2. So if I have the capacitance, in order to keep the charge constant, I have to double the voltage. So it was 200 volts, now it's going to be 400 volts. Consider this circuit. All three capacitors are identical. What is the voltage across C2? Okay, well, these two give me a capacitance of 2C, assuming they're all the same, right? And then I would have a circuit that would look like this. One capacitor C, one capacitor 2C with 12 volts. And I'm asking, what is the voltage across here? That's going to be the same as the voltage across here. This has twice the capacitance, so it has half the voltage of the other. So I'm going to have 4 volts, and 8 volts over here. So the answer is 4 volts. What is the equivalent capacitance of this circuit? Okay, I start with these two. That's 1 over 4 plus 1 over 4. That's equal to 2. And then I combine that with this one. That's the 2 and the 2 is 4 microfarads. And then I'm left with a 4 in series with a 4. That's 1 over 4 plus 1 over 4. That's equal to 2 microfarads, so C is the right answer. A flat iron is marked with a voltage 120, power 600, and normal use the current is what? Okay, well, I know P is equal to V times I, so I is P over V. That's 600 over 120. That's equal to 5 amps. All right, which of these statements about the use of voltmeters and ammeters is correct? Voltmeters have a large resistance and are connected in parallel. That is correct. Voltmeters have a small resistance. Okay, that's not correct because they don't have a small resistance. Ammeters have a large resistance. They actually have a small resistance. That's not correct. Ammeters have a large resistance. That's not correct. Also not correct because they're connected in series. And voltmeters have a small resistance and are connected in series. They don't have a small resistance and they're not connected in series. So it looks like B is the only correct one. 2 space heaters in your living room are operated at 120 volts. Heater 1 is twice the resistance of heater 2. Which one will give off more heat? Or more particularly, which one has more power? Because that's a measure of the heat that it gives off. Well, the one with the smaller resistance has the bigger power. All right, they both operate at 120 volts, and so I know that power is V squared over R. So if R is small, that means P is big. You can think about this too, that the smaller resistance, it resists the flow of electricity more, so it's going to have a bigger current, and that's going to deliver more power to my device. When you apply a potential of 3 volts to a particular electrical device, the current is 2 amps. When you apply 6 volts, the current is 3 amps. Is this ohmic or non-ohmic? Well, when I have 3 volts, I have 2 amps. That is a resistance of 3/2 of an ohm. But when I have 6 volts and 3 amps, that's a resistance of 2 ohms. So my resistance changes with the potential that's across that resistor. That is a non-ohmic device when your resistance actually changes. 1 volt potential difference is observed across a 10 ohm resistor. What is the current? Okay, well, I is V over R. I have 1 volt, 10 ohms, 1/10, or 0.1 amps. Okay, let's look at this. I have 2 capacitors in series. Each capacitor has plates given with the area given and the distance. And one of the capacitors, C2, has a dielectric constant of 2. So I have these 2 capacitors, C1, C2, and this one has a dielectric in the middle with a kappa equal to 2. All right, now I can figure out what are the capacitances of these two. C is equal to epsilon naught A over D. This, by the way, is going to be for C1. That's 8.85 times 10 to the minus 12 times A, which is 0.004 over D is 3.54 times 10 to the minus 8. And I get 1 times 10 to the minus 6 farads. That's 1 microfarad. All right, so here I'm going to have 1 microfarad on this capacitor. And because this one has a kappa of 2, is that what it was? Yeah, the dielectric constant is 2. That's going to be 2 microfarads for this capacitor. All right, the equivalent then is 1 over 1 plus 1 over 2. That's 1.5. That's going to be 3/2. The inverse of that are 2/3 of a microfarad. If they're connected to a 12-volt battery, what is the charge on each? Well, the charge on each is going to be equal to the charge on the equivalent, which is going to be the equivalent capacitance times the voltage. That's going to be 2/3 times 12 That's equal to 8 volts. I mean, excuse me, not 8 volts, 8 microcoulombs. So each of them will have 8 microcoulombs. 8 microcoulombs. If you remove the dielectric, does the charge on each capacitor increase, decrease, or stay the same? All right, so if we remove that dielectric, what happens is this now becomes 1 microfarad, and then this now becomes 1/2 microfarad. So the equivalent capacitance decreases. That means that the equivalent charge decreases. All right, so both of them will have an equivalent charge actually of 6 microcoulombs. So the charge Q1 will decrease and the charge Q2 will decrease. They have the same charge, so they have to both do the same thing if they're going to change. All right, consider this configuration of charges. What is the potential at the location of the +2 nanocoulomb charge? I want to know the potential. No, the potential right here. Okay, so V is equal to the sum of the individual potentials, and at this position it's going to be equal to the potential due to this charge plus the potential due to that charge. So that is going to be K times -5 times 10 to the -9. So let me go ahead and write all these out. 9 times 10 to the 9th, that's K, times Q, which is -5 times 10 to the -9, divided by R. That's this distance. Notice 3, 4, this is 5 meters, divided by 5 meters, plus 9 times 10 to the 9th, 8 times 10 to the -9, divided by 4 meters. So let's see here, I can cancel some things. The 5 cancels there. This cancels with that. So this is equal to, the first one is just 9. And then this cancels with this, leaves a 2. -9 plus 18, that's equal to 9 volts. So the electric potential at this point is equal to 9 volts due to these two charges. Now let's also look at what is the potential energy contained within this configuration. In order to do this, I'm going to take the potential energy of all of these things. So I want to take what is the potential energy of these two charges, potential energy of these two charges, and the potential energy of these two charges. All right, so here, potential energy, member, equal to KQQ over R. So let me go down here. I'm going to have for the first one just K. That was a -5 nanocoulomb, a 2 nanocoulomb, divided by the distance between them, which was 5 meters. All right, that's KQQ over R. And then I can find that potential energy. That cancels there. I get -18 times 10 to the -9 joules. All right, and now I want to do the 5 and the 8. That 5 coulomb charge is negative, and then I had a positive 8 nanocoulomb charge. divided by the distance between them, which was 3 meters. This cancels with this, gives me 3. This with this, so I get 3 times 5 is 15 times 8. What's that? 80 plus 45. 125 times 10 to the minus 9 joules. And then I want to find this for the 2 and the 8. There's my K. Divided by the distance between them, which was 4 meters. And then this is equal to, let's do my cancels here and here. This 4 cancels with this 8 and leaves a 2. That gives me 36 times 10 to the minus 9 joules. And then so I just add up all these. These are all, I'll just make them into nanojoules. So I have negative 18 plus 125 plus 36. That's 125 plus 18. That's what, 143, if I've done my math there right. That's in microjoules, so that's the answer. That's the potential energy that's contained within that configuration of charges. Okay, so here I have a basic parallel and series circuits. I want to know the current and voltage for all of these. It can begin by finding the equivalent resistance. Here my equivalent resistance is, I have a 1, a 2, and a 3, so that's going to be 5 ohms of my equivalent resistance. So this would be an equivalent circuit that looks like this. Or excuse me, not 1, 2, and 3 is 6 ohms with 12 volts. That means I'm going to have 2 amps going through this circuit. So I have 2 amps through each of these. These resistors in series have the same current. And then the voltage is just I times R for each of these. So 2 amps times 1 ohm is 2 volts. 2 amps times 2 ohms is 4 volts. 2 amps times 3 ohms is 6 volts. And that adds up, by the way, to 12, as it should. And then here I want to know the current and voltage. Now these are in parallel, so they're both going to have the same voltage, which is going to be 12 volts. And if I want to find the current, I just say V over R is equal to the current. So that's 12 over 3, which is 4 amps, and 12 over 6, which is 2 amps. And that's the answers for those. And then I have this particle that's given by this function. I want to know the electric field. Well, I know that the electric field in the S direction is negative del V del S. Del S, excuse me. So here, my E in the X direction is going to equal to negative the partial derivative of V with respect to X. So that's negative 3y squared minus 2y. That's the X direction. And then in the Y direction, negative del V del Y. The partial derivative of this is going to be, actually I made a mistake here. This should be negative 3y squared minus 2y. So this is going to actually be negative 3y squared plus 2y. And here it's going to be negative of this, which is going to be 6yx minus 2x. That's the partial derivative with respect to y, which of course is negative 6yx plus 2x. And then if I put in my coordinates x equal 1, y equals 1, this is negative 3 plus 2, that's negative 1. This is negative 6 plus 2, that's negative 4. And so my electric field in vector notation, which is going to be the answer, is equal to, my electric field is negative 1I minus 4J volts per meter and newtons per coulomb. Okay, let's look at this number 19. I have this circuit, and I want to find what is the voltage and the charge on all of the capacitors. So let's just redraw it first. Let's see, I'll redraw it right here. I have a 12-volt battery. I have the 6 microfarad right here. That's C1. And then here I break into 2 branches. I have a 4 microfarad here. And then I have, coming up here, I break into 2 more. I have a 2 and a 2. Now in this bottom branch, I have just a 1 microfarad. And then that all goes back. And now I want to find the equivalent. Let's see, I'm going to start with this 2 and 2, which is equal, of course, to 1. So if I redraw this, I have my 12, my 6, a 4, and a 1. Excuse me, not 1. This is 4 microfarads. 4 microfarads. And then this is a 1 microfarad. And then that goes back. This is my 6. Now I combine these two. A 4 and a 4, that gives me 2 microfarads, 1 microfarad. Alright, this is 6. And then I combine these two and I get a 3 microfarad. 2 plus 1 is 3. Volts. And then I can keep going. 6 and a 3, that's a 2. And that's my equivalent capacitance. Alright, so that's 2 microfarads. I have 12 volts here. Alright, now I want to start stepping backwards. So here I have 24 microcoulombs. That's Q equals C times V is 24 microcoulombs. Because these are in series, I'm going to have 24 microcoulombs here and 24 microcoulombs here. Alright, so let's see, this is actually C1, so this is going to be 24 microcoulombs. And then I can also find V for these. V is Q over C, so I just divide these two, and that's equal to 4 volts. So here I have 4 volts, and over here I have 8 volts. Right, so if that's 8 volts, then I also have 8 volts here, and 8 volts here because they're in parallel. So let's see, this capacitor is C3, so that's going to be, V3 is 8 volts. And then the charge here is going to be C times V. That's 1 times 8, or 8 microcoulombs. Alright, so now if I have 8 volts here, I have a 4 and a 4 that share that voltage. So this is 4 volts and 4 volts. 4 plus 4 gives me that 8. And they're identical capacitors, so they have the same capacitance, or same voltage. Now, this capacitor is the same as this one, which is C2. So I have 4 volts here. Across a 4 microfarads, so I have 16 microcoulombs. And now I want to look at this capacitor, which has 4 volts. That's the equivalent for these two. So I have 4 volts across this one and 4 volts across this one. That's V4 and V5. Both of them are 4 volts. They're each 2 microfarads, so they both have 8 microcoulombs each. Right, and that's the, oh, and then E5, well, I have this information for E5. E is 1/2 CV squared, so that is equal to 1/2 of C5, which was 2 microfarads, times V squared 4 squared. Half of 2 is 1. That's 16 microjoules.